overview of graphing and concavity and increasing and decreasing. Is everything all put together? So this is just kind of an overview. I'm not really going to talk through this. This is just something I took out of the book that kind of tells you when you're doing graphing and using calculus to help you, some of the things that you do. Okay, so I'm going to go through that. Let's start down here. This is sort of a good problem to go over because this tests to see how well students understand the language of what we've learned and what a sign chart does and everything. So what we're going to do is, based on this information I gave you, we're going to do a graph, okay? So it's going to kind of go like this then, all right? So first of all, everybody good? Okay, so first of all, the information on this, the domain's all real numbers. So if the domain's all real numbers, that means there's no breaks in the graph, okay? It's continuous everywhere, so we know that, okay? Then we got this statement right here, and this statement says, as x goes to infinity, the graph levels off at -3. So that would kind of be like a horizontal asymptote at x equals -3. So we're going to kind of piece this together as we do this then. So let's go ahead and down on the graph I gave you, go ahead and just take it out maybe to about -3 in both directions, and the same thing on the y-axis like this. Okay, and we'll kind of just piece this together as we go through this. Okay, and these problems are thoughtful. They make you think a little bit. So anyway, what this statement right here says is it says you have a horizontal asymptote at x equals -3. So you want to go ahead and just put your dashed line. We've talked about certainly what horizontal asymptotes are, so we have that. Now what that's going to say about this graph is it's going to say that when x goes to, that's a negative infinity. That means that the graph is going to kind of level off like that. I'm not ready to draw that yet, but what's going to happen is the graph is either going to level off above the asymptote or below the asymptote. It's going to do one of the two, because that's what that statement says. Does that make sense to everybody? If the limit goes to negative infinity and it's a value, that means you've got a horizontal asymptote, okay? So this is almost the same thing. This is just saying as you go infinitely to the right, then it levels off at 3, so that would tell you you have a horizontal asymptote at x equals +3. So what we'll do on the graph is the same thing. We're going to draw a horizontal asymptote through 3 like this. And again, what this is saying is as the graph goes to infinity, the graph levels off. Now, I don't know if it's going to be above or below. We'll get to that in a minute, but that's what this problem says so far. So the domain's all real numbers. There's no breaks. We have 2 horizontal asymptotes. Okay, does that make sense so far? Okay. All right. Now what we're going to do is we're going to look at this. This is a table of values right here. So, and I'm going to zoom on this a little bit so I can see this a little bit better. So all this is this is a table of values. So we're just going to plot points. Okay, this table right here, that information right there just means we have a point -2, 0. So what are you going to do? You're going to plot a point -2, 0. Okay, that's a table of values. Then this says we have the point -1, 2. So we do the same thing. We just plot a point. Okay, then we have 0, 0 as a point. So we plot that. We also have 1, -2 as a point. And finally, we have 2, 0 as a point. So that just gives you some points on the graph. You can kind of begin to see how this graph's going now if you look at this. Okay. Now, the sign charts are the calculus part right here. So what this is this part right here, this is a first derivative. So the first derivative, what it does is it tells us where functions are increasing and decreasing. That's what your sign chart does. So let's see if we remember this stuff. You want to have this, get this down as soon as possible. If the first derivative is positive, what does that tell you? Graph's increasing. What does that tell you? Decreasing, okay? Now that means no derivative. Now no derivative, what if we talk about no derivative? You could have a sharp point. You could have a break in the graph, but we don't have a break in the graph. because the domain's all real numbers. So it's got to be a sharp point, see? Okay, you got to kind of put all this stuff together. So what I want you to write on your notes, just write yourself a note. That would be you're increasing, then you're decreasing and decreasing there. And then you might want to make a note that that's kind of like it's a sharp point is what that is. That has to be, because that ND stands for no derivative. And then we increase like this, okay? All right, so we have that. Now the next thing is, this is the second derivative, okay? And the second derivative, we talked about this last class, okay? The second derivative tells you about concavity, okay? And we'll be kind of reviewing that quite a bit as we go today. So what I taught you last time, if you weren't here last time, one of the easiest ways to remember about concavity is this little diagram, okay? The happy face means you're concave up, okay? My happy guy has a second derivative tattoo on his cheek. So if it's second derivative and it's positive, you're happy, okay? So it's concave up, okay? That's an easy way to remember this. If it's negative, then you're concave down. Okay, and that just kind of tells you a little bit about the shape of the graph. All right, and this is real easy to remember with that diagram like that. So anyway, what this would mean is you would be concave down there. No, teacher. Concave up, you're happy. Okay, so that would be concave up, concave down, concave up, and then concave down again like that. Okay? And if the second derivative doesn't exist, you don't really have to worry about that or anything. We've already established that's just kind of a sharp point anyway, okay? All right, so now what we're going to do is try to put this all together, all right? So it goes like this. These things right here, you want to make a note of this also. These are places where the concavity changes. So those things are called points of inflection. And points of inflection are places where the concavity changes, okay, from up to down like that, all right? So what we're going to do on this then, it doesn't have to be totally accurate. Let's just kind of start with this sign chart right here. Now what we know is we know this thing levels off at that horizontal asymptote. Now what it's going to do is the function's going to increase until it gets to -1, okay? Then what it's going to start doing is it's going to start decreasing. Then you've got that sharp point right there. Then it's still going to decrease. Then it's going to change directions and increase, and then level off like that. Okay, so if you look at what that sign chart says again, it's going like this. Increase until you get there. Decrease, no derivative, so sharp point. Okay, then it's still going to decrease. And then it's going to start increasing again like that. Does that make sense? Mm-hmm. Well, that's what that sign chart says. Okay, so what you're going to do is just go ahead and sketch this out like this. Okay, let's just kind of do this like this. I'll do the final thing in orange here. So it goes like that. Okay, it goes like this. Now that would be not a sharp point. It would kind of be, a nice smooth point like that. So it's going to go like that. We're increasing until we get to -1. Then we're going to decrease. So it kind of changes directions there. And then it says we decrease some more. Well, that's kind of interesting. That can't be a sharp point then. If it decreases -1 to 0, then it does that. Here's what it's got to be. Okay, there's one other possibility. Okay, it can't be a sharp point because it's going to keep decreasing. What's another possibility for a graph where the derivative doesn't exist? We don't talk about this very often, but it exists.
When it's undefined?
The tangent line's vertical.
Yeah.
Okay, all right, so that's what that is. No cusp. I thought it was going to be, but it didn't. Okay, so it's going to have to go like this then. All right, so sometimes on these problems you got to kind of put them together as you go. So it's going to go more like this. Okay, you're going to end up having kind of going straight through like that. Okay, just kind of go like that. Then the rest of it you can go through and put together kind of like that then. Okay, so that's got to be a vertical tangent line on that then. All right, so again, what this said is we're increasing until we get here, then we're decreasing, but there's no derivative. The only possibility is that line is a vertical tangent line. then it decreases until you get to 1, then it increases the rest of the way. Does that make sense? Yeah, shake your head or something. Okay, all right. Now the concavity goes like this. So the other thing we want to do is locate these points of inflection. So when x is -2, you want to just put like a little, maybe an x through that. That's where the concavity changes. The other place where the concavity changes is 0, so let's put a little x there, and then it changes it to like this. Okay, so this is what I also want you to see. Okay, the sign chart for concavity says we're concave up until we get to -2. So does that look like kind of a happy, half of a happy face? Okay, that's good. Then it says we're concave down from -2 to 0. That's a frown, right? So that's concave down. Then we're concave up from 0 to 2, so they're happy again, and then concave down. So it's concave up, concave down, concave up, concave down. So that graph satisfies all the conditions of that problem. All right, does that make sense? Okay, so you got to put all that together. Just kind of carefully, you got to know what all of those things mean, in particular that sign chart. So is there any question about that? Okay, these problems are not easy for students because they really kind of check your knowledge of all the things that we've learned so far about sign charts and concavity and stuff. Let's go next page. Next page, kind of basic. You'll have a little bit of this on your homework. Typical kind of a future test question. I give you a graph. You answer all the questions about the graph. Okay. So let's see. To begin with on this, let's just kind of go through these first ones right here. And you got to, again, know what all these things mean. Okay, so what this is saying is the first derivative is negative. What does that tell you about the graph if the first derivative is negative? Function is decreasing, exactly. Okay, so that's what that says. This one says the first derivative is positive, so what does that tell you? Function's increasing, okay? So that's what you're really looking at, and the problem is this. Well, let's see. One good way to do this is let me just kind of shade on here. Let me pick a color that'll show up like this orange or something. Let me find all the places where the function decreases. So from there to there, the function's going to decrease. The y values are getting smaller. From here to here, the function's going to decrease. And from here to here. Okay, so that's clearly where the function decreases. So what we need to do is we need to just name those in an interval then. And we name them with the x value. So this part out right here would be -infinity until you get to b. Always name this with intervals, and always make the intervals open whenever it's increasing and decreasing. That will always be parentheses. And then this one is going to be 0 to e. And use the union symbol on that. Okay, and then the next one is going to be from E to G, like that. So that names the three intervals where you decrease. Okay, does that make sense? Okay, all right, yeah.
Why not have like 0, I guess the second where you said 0 to E, why not M to E?
Okay, are you talking about putting it in one interval?
No, but like you have the value of 0,
Uh-huh.
so everything else up there is letters, right? And there's a horizontal tangent line that says M.
And I think that M is a y value.
Okay.
I think that's what that is. And yeah, it's just 0 is where that is. I see what you mean. Okay. All right. All right, now the rest of it is where do we increase? So we would increase here. So we would be increasing here from, and that would be B to D, I guess. Okay, so we're increasing there. We would be increasing from D to 0, it looks like. Okay, and then finally out here, that looks like, you know, from G forever, then the graph is going to be increasing like that. Okay, so again, always name your intervals with x values, and it's pretty easy to tell where a graph is increasing and where it's decreasing. And don't forget what this means. When you're decreasing, the tangent line has a negative slope. That's important. when you're increasing, the tangent line has a positive slope. That's the calculus that we talked about, okay? All right, well, these are the same answer then. So basically, B and C are the same answer, okay? So you can just kind of, if you want to write that, you can just rewrite it. It's the same as B. And then A and D are the same. That's just where the function's decreasing, okay? So a lot of times I ask the question that way just to see if students understand that they're asking the same thing, okay? All right, so now the next thing we're going to look at is local min and local maximum, okay? So a local minimum, remember a local minimum has to be a place where the function decreases, hits a low point, then starts increasing. Okay, a local maximum's the opposite. The graph that's not a maximum, teacher. It goes like this. Increases, then decreases like that. Okay, so let me ask you a question, simple question. How many local minimums do you see on this graph? There are 2, good. Okay, so the local minimums are going to be there and there, okay? And we're just going to name those with x values. So that would be at x equals b, and the other one would be at x equals g. Okay, like that. Okay, how many local maximums does this graph have? It just has 1. There's only one place where the graph goes uphill, hits a high point, and goes downhill, okay? And that would be at 0. So the local maximum is just at x equals 0, okay? So that's what that is so far. That's kind of an overview, really, of what we talked about in section 11.1. Okay, now the rest of this, we start getting into the second derivative. So when you get to g, this is saying the second derivative is negative. Okay, well, what did that tell you? Remember the happy face, sad face? Second derivative is negative. What does that tell you about the graph? Concave down, exactly. So this problem right here is just saying, where are you concave down? Okay, part H is saying the second derivative is positive, so that's saying, where are we concave up? Okay, so that's what we need to do on that, and see, basically I and J are going to be saying the same thing, okay? So let me kind of go through and do this like this. Let me just sort of erase what I have up here. And let me go back up to the graph, and then we'll do this then. Okay, so I'm just going to pick let me just highlight this or something. Okay, so here's how this goes. The concavity is always harder for students. So concave, I'm going to do concave up in yellow. So that would be from there to there. That's a concave up shape. This thing right here is what we call a point of inflection. That's just because the concavity changes. Point of inflection. Okay, so that's concave up. The other place I see that we're on concave up, it'd be right here. Okay, and then concave down would be this piece, and that piece right there. Okay, so concave up, what happens on concave up is this, and this is sometimes hard for students to grasp immediately, but what happens on concave up is the slope of my tangent line is going to get bigger. Right now I have a negative tangent line, right? Now it's a 0 tangent line. Now it's positive. So concave up technically means the derivative or the slope of the tangent line is getting bigger, okay? Concave down means the tangent line is getting smaller. The slope's getting smaller. Another way to look at it is this way. See, in concave up, see how my tangent line is below the graph? Concave down, I'm above the graph. That tangent line's above the graph. That's how you can distinguish between those two things. Okay, so here's how you would name this then. So concave down would be this part right here. That would be negative infinity until we get to A. Okay, negative infinity to A. No, I'm doing the wrong thing. I'm saying the right thing, but writing the wrong thing. So negative infinity to A, like that. And then the next place would be the part in the middle, which would be from D to E. Okay, so you'd have that. And then finally, you would have H to infinity like that. All right, so that would be the places where you're concave down. Concave up would be the things I highlighted in yellow. So that would be, it looks like A to D, and also E to G. Or no, E e to h, all the way e to h, okay, like that. Okay, so the points of inflection, a lot of times I just highlight these. The points of inflection, I'm going to put a little X by that. Okay, there's 2 points of inflection like that. Okay, that's where the concavity changes. Okay, now really on this, we've already answered these 2 questions here. So concave up is where the first derivative is positive. So that would be the same answer as you got on H. And you can just write same as H if you want to, or just rewrite it. And then concave down would be where the second derivative is negative. So that would be the same as G. Okay? So that's how it goes like that. Yes?
So you said if it's concave down, the tangent line is above.
Right.
And then if it is concave up, it's below.
Yeah, that's a good way to think of it, because
Okay.
it's kind of like if you have a shape, kind of like this. Okay, a point of inflection is where the concavity changes. So what will happen is the tangent line here is really always above.
Yeah.
When you get there, it sort of slices through it. Part of the tangent line's above, part of it's below. And then when you're concave up, that tangent line's below, and then this point of inflection, which is kind of hard to tell where it is, it's kind of part of it's up, part of it's below, part of it's above. So that's one good way to look at that too. Okay? All right, so points of inflection. Now, what a point of inflection is that's where the concavity changes. So really on this graph, A is a point of inflection, and so is H. So this changes from concave down to concave up. Over here, concave up to concave down. So there's only 2 points of inflection, and that occurs at x equals A, x equals H. Now let me say one other thing about this too, is although the concavity changes at D from up to down, that's not a point. The function's undefined. A point of inflection has to be a point on the graph. It has to be. So that's a point, that's a point. That would be your 2 points of inflection. Okay, does that make sense? Okay, all right. And the last thing is the horizontal asymptotes, okay? Horizontal asymptote, does this have a horizontal asymptote? Yeah, this line right here, okay? That looks like y equals L, okay, is what that is. And vertical asymptotes, does this graph have any vertical asymptotes?
Yes.
D and E, right? Okay, so you have a vertical asymptote at D and one at E. Okay, so we would say on that, we're going to say x equals D and x equals E. So see, that problem is an overview of all the things we've learned about graphs, okay, with concavity and mins, maxes, increase, decrease, points of inflection, everything. Yeah.
At the point of inflection,
Okay, it has to be a point on the graph, and it's a point where the concavity changes from up to down or down to up. Okay, so if you look at this graph, there's only 2 points on the graph where the concavity changed. Right there, it changed from down to up. Okay, that's what that is. And over here, the concavity changed from up to down. That's a point on the graph. Now see, this is not a point of inflection, even though at D, the graph changed from up to down, but that's not a point. That's an asymptote.
how about B? The B.
The what?
The B.
No, that's your concave up there. See, this whole thing right here is concave up. You're concave up from A to D. So that's not a point of inflection. Okay, one other way to look at a point of inflection is like this. Right now, the tangent line is above the graph. You see what I mean? My tangent line's above. What happens when you get to that point of inflection, the tangent line kind of slices right through the graph. Now it's below the graph. Okay, so what happens is you're changing from down to up. Over here, you're changing from up to down. Okay, that you're looking at a minimum there, is what you're looking at. That's not the point of inflection on that. Okay?
So,
Yep.
how come, I'm kind of confused why, I guess 0 wouldn't be an inflection point if it's going.
Okay, because the concavity is concave down from D to E. The concavity is not changing there.
Oh, okay.
Okay, it's only where the concavity is changing. That's why I was trying to use highlighters. See, that you're down, now you're up.
Yeah.
You're up, now you're down. Okay, that's just a place kind of like wherever the concavity changes. See?
Yeah.
Okay, so that would be concave down, then concave up. Okay, that's what that is. Okay, that's the point on the graph where the concavity officially changes. Okay, you got that?
Yeah.
Okay. Okay, so let's do this graph on here. I want to do that, and then we'll kind of get into functions where we kind of crunch out derivatives and put this all together. So again, these problems right here are good to give students to see how well they understand language on this. So we're going to try to put this whole thing together. Okay, first of all, the first statement says that the domain is all real numbers except x can't be equal to 1. So something's happening on this graph at 1. We don't know what yet. There could be a hole in the graph. There could be an asymptote. Just it's undefined at x equals 1. So that's basically what we know from that statement is undefined at x equals 1. So we'll keep that in mind as we move on. Okay, these two statements right here say the same thing. This is the easiest part of the problem. So if I give you f of 0 equals -2, that just means you have a point 0, -2 on the graph. So 0, -2 is on the graph. Now you have to understand what that language says. Same thing here. What does f of 2 equals 0 tell you? That tells you that you have a point 2, 0. Okay? The thing in parentheses is x. The answer to a function is a y value. So let's go ahead and let's start putting this together then. Let's go ahead and just go out to 2 and out to -2, and then maybe up to 1 and -1 for now. So what we're going to go ahead and do is just let's put these 2 points on your graph. So we have 0, -2, right, is what that one is. So I need to go down probably one more. Okay, so I'll put the point 0, -2 on there, and then I've got the point 2, 0 like that. All right, so that's all I got so far. Okay, well, right now we know that the graph's undefined at 1. We'll figure out why in just a minute. Okay. All right, now if you look at this statement, all right, let's see if we know what we're talking about on this. All right, so if f prime of x is less than 0, what does that tell you about the graph? If the derivative's negative, what does it tell you? The function is decreasing, right? So this statement right here just tells you that you're decreasing at -∞ to 1 and 1 to infinity, okay? So we got that. So we know that the function's going to be kind of decreasing like this, right? So one possibility would be for this graph, you can kind of think in your mind kind of how it might look something kind of like that, but we'll kind of move on and try to put this together here in just a minute. Okay, what's the next statement? Hold on, I'm not quite ready to do that yet. So we know we're decreasing on that then. Okay, let's look at what this is. This is the second derivative. So if the second derivative is negative, what does that tell you? Concave down. Okay, so we know we're concave down on this part right here. That just means the graph is going to kind of look like either like that, like this, or like this. Now, I always think students do better on these problems if you understand concave down can look 3 different ways. It can be like a whole U shape, like a whole frown, or it can be half of a frown. Okay, so it can either be this, this, or this. So that's what that is. What does this statement say? Second derivative is positive. So what does that tell you? That's your concave up. Okay, so concave up is going to mean that you're totally happy, okay, like that, or you're halfway happy. Okay, like that. It's got to be one of those 2 things like that. All right, so we got that. We're not quite ready to do the graph yet, but we know where we're decreasing, where we're concave up, and where we're concave down. Okay, now the other thing it says is we have a vertical asymptote at x equals 1, so that's easy. Let's go ahead and put a vertical asymptote at x equals 1. And then it also says we have a horizontal asymptote at y equals -1. So we'll go ahead and put that together like this then. Okay. All right, now we're ready to try to put this together, okay, based on everything we have. Well, let's see. First thing is, it says we're concave down. Let's look at this. From negative infinity to 1, you're concave down. So in this region here, you're concave down. So that means it's either going to look like this, or like this. Okay, well, think about how that's going to have to be. It's going to have to go through that point. What happens to a graph when it approaches a vertical asymptote? Where does the graph go? Either goes down or up. So does it make sense that that's going to have to go down? Okay. What happens to a horizontal asymptote? That means the graph levels off at it. So that's going to have to go like that. So imagine this part of the graph going like that. Is that concave down? Yeah. Okay, so that's how that's got to go. All right. You got to think through it. Sometimes you got to trial and error this a little bit too. Right? So we would end up having this part of the graph's going to go like this. And then that'll establish what we're supposed to. Now the other thing the problem said is the function is decreasing from negative infinity to 1. Is this decreasing?
Yeah.
Yeah, okay, so it's concave down and it's decreasing. So we're good. Okay. So the other thing is concave up from 1 to infinity. Okay, so if you're concave up in this area, it's either got to be a full smile or it could be like half of one, kind of like that. Okay, so what does the graph got to do here when it gets close to that asymptote? It's got to approach it, right? Okay, then the thing's got to level off like that. Okay, so the only way you could do this, remember we're concave down. Is that concave down if I go like that? Yep. This way, that's half of a frown. That's that's concave up.
Yeah.
I think I said said that backwards, so we're concave up. Sorry about that. Okay, so yeah, we're concave up, so the graph would have to go like this. Then it would have to level off at the horizontal asymptote like that. All right, so let's see if this looks right to us. So is that concave down? Yeah. Concave up? Yeah, that's good. Decreasing, negative infinity to 1, we're decreasing. 1 to infinity, we're decreasing. So that looks like that's what the graph has got to look like. Okay?
So you say when it's concave down, it's below or above the graph?
The tangent line on concave down is above the tangent line. Like that. Concave up, the tangent line is always below the graph. Like that. Or think of your concavity like this. This is the best way to look at that. Is concave down, there's 3 ways the graph can look. Concave up, there's, I think I put one wrong, kind of like this. It kind of go like this. Okay? Those are the possibilities. It doesn't have to be the whole happy face. It can be half of it. Okay? All right, what do you think? You guys understand what I did? Maybe easy when I do it. It's hard when students do this. It takes a little bit of work, and there's some trial and error in it. There just is. Okay, but what that's attempting to do is see that you understand all the symbolism and what all the calculus is telling you. Okay. All right. Well, let's see. Let's go down to this next thing here. Now, this is kind of where we're putting everything together. This problem right here, we're going to do the. I'm not going to actually in class do the first and second derivative. I'm just going to give you what they are because that's a little bit time consuming. But on this one, what we're going to do is use calculus to graph this function. Okay, we're not even going to touch our graphing calculator until we're done with the problem. Then we'll see how accurate we are. Okay, so the first thing is when you're looking at the domain on this function, you're going to look at what, try to figure out what makes the denominator equal to 0. Okay, so we're just going to do this. Just write down the denominator is x squared minus 9 equals 0. Okay, so we know we can't divide by 0, so we need to do that to kind of figure out where our asymptotes are and everything. Okay, well, you can solve this equation either by factoring or add 9 to both sides and take the square root. It doesn't make any difference. I'm just going to do it this way. I'm going to move the 9, do square root of both sides. So that gives x equals plus or minus 3. So what this means is the domain we can write just as set of x is not equal to negative 3, and it's not equal to 3. So something's going on at -3 and 3. You're going to end up having vertical asymptotes is what you have. Okay? All right. So we have that. And the vertical asymptote, what you want to do on that, it's always the same thing. It's just set the denominator equal to 0. So the vertical asymptotes equations are going to be x equals -3 and x equals 3. So that's what we know about our graph so far, is we have vertical asymptotes at 2 places. Okay, that's it so far. That's what we know. Okay, now if you want to do a horizontal asymptote, there's 2 ways to do this. You could either do this in your head, if you remember this, or you could do the limit as x goes to infinity. It doesn't matter. It's your call. Okay, so now we did L'Hopital's rule in class last week, which you could do if you wanted to. You don't have to. Do you guys remember by looking at that what the horizontal asymptote is?
3.
It's 3, right. If the degree of the top and bottom are the same, the exponents are the same on top and bottom, then it's 3 over 1. Okay? So you can just apply that rule if you remember it, and I hope you remember it because that's the easy way to do that. So we would just say y is equal to 3 over 1, or y is equal to 3. So we do have a horizontal asymptote on the problem then. All right, that's it. Okay? So when you're dealing with this kind of problem, figure out asymptotes. Okay? If you have a rational function, that's a function that looks like this where you have a fraction. Okay? Okay, now we're going to go to the intercepts. Okay, the way you find an x-intercept is you just set the function equal to 0. The way you find a y-intercept is you set x equals 0. So it's just the opposite variable goes to 0. So what you do to find an x-intercept is you want to write down the function I gave you, and then you want to set that equal to 0. Now we're going to solve this equation. Okay, here's algebra background stuff that pops up. You want to get rid of that fraction. What do you do to both sides of the equation so the fraction goes away? Multiply by x squared minus 9. Exactly. Okay, that's something you want to kind of train yourself in. I'm solving an equation. My equation has a fraction. That's what I always try to do. Okay, so what that would end up being then is that would end up giving you 3x to the second plus 2 equals 0, and then we're going to solve this particular equation. Okay. Okay, well, this one doesn't factor. You would just have to move the 2 to the other side, so you would get 3x to the second equals -2. Then you would divide by 3, so you would get x to the second equals -2 over 3. Okay, what do you do now? Square root of both sides, good. Something weird happens. What happens if you do a square root of a negative number? You don't get anything. So that basically this has no real solution. Okay, so that just means that we do not have any x-intercepts. Okay, the math will tell you that. Okay, so you don't have to have x-intercepts. This problem doesn't have any because of that. Okay, so that'll happen. Okay, so now on the y-intercept, what you want to do is you want to evaluate the function at 0. So you just take the function, and everywhere you see a x, put in 0. So you'd have 3 times 0 squared plus 2 over 0 to the second minus 9. The numerator would be 2. The denominator would be -9. So your y-intercept is the point 0, -2 ninths. Okay, so that's another key thing we have. We have 1 point on the graph now. Okay, all right. So x-intercept is always done the same way. Set the function 0 and solve. Either you get an answer or you don't. Okay, y-intercept's always the same way. Let x equal 0 and do arithmetic. Y-intercepts are easier than x-intercepts. Okay, are you with me so far? Okay, all right. Now, what we're going to do on this now is I'm going to give you the derivatives. What I had kind of intended to do on this is give you the derivatives. Okay, I'm not going to go over that. You would use the quotient rule. So I'm going to give you these derivatives. So you want to write down on F, the first derivative is -58x over x to the second minus 9 to the second. And that's just by the quotient rule. Now we've done that a ton. That's why I'm not going to do that. Okay, you can verify it if you want to. Okay, when class is over, you can verify it if you want to. That's what you get. I'm going to do the same thing on the second derivative. The second derivative, you would just take the derivative of the first derivative by the quotient rule. And let's go ahead and let's actually at least set this one up. I'm not going to go through all the details of this, but what you would do is you would do the bottom, x squared minus 9 to the second, times derivative of top, which is negative 58, minus, and then the top would be negative 58x, and then the derivative of the bottom is a chain rule, which would be 2 times x squared minus 9 to the first, times derivative of what's inside 2x, all over the bottom squared. And the bottom would go x squared minus 9 to the second like that. So I just want to remind you of the setup of that. Again, what we're doing is this. So bottom, derivative of top, minus top, derivative of bottom over bottom squared. Now, I'm not going to do the simplification on this. I'm just going to say by magic, and you could do this. I mean, it's just basic multiplying stuff out. It's not hard to simplify this. What you would end up getting is you would get 174 x the second plus 3 over x the second minus 9 to the third. So, I mean, I'm not going to take the time to do all the derivatives on these problems because the point of this is that you can do the sign charts and all that kind of stuff. All right? And you got to work on that a little bit. Sometimes that second derivative can be a little complicated, but it's all algebra going on in there. Okay? So that's what you would get on your derivatives. Okay? Both of them are quotient rules. Okay, now let's do a sign chart because that's the key thing that we're going to do on this then. So we're going to do a sign chart for the first derivative. All right, now what you want to do with this then is you want to do this. So first of all, when you do a sign chart for the first derivative, you do two things. Okay, you want to look at, you want to set the first derivative equal to 0. And we're going to find what we call critical points. Critical points are where the derivative is 0 or undefined. So we're going to do this, and you can learn to do this in your head in a lot of situations. Okay, so that's the first derivative that you would get if you did the quotient rule. And then what we're going to do is just solve that equation. So again, you can do this in your head. What you would do is you would get rid of the fraction. And you can actually don't have to write that step because you know what's going to happen. You know that's going to cancel anyway. So what you get is you get negative 58x is equal to 0. And then you can solve that equation. So what you end up getting is you get x equals 0. Okay, and that will be a number that we're going to use in our sign chart. Okay. The other thing that we have to ask is, where is the first derivative undefined? Okay, and that's real important on this. Where is it undefined? Well, it would be undefined where the denominator is 0. And you can again do this in your head, so it's where that denominator is 0. Now, I hope you can do that in your head. What are the two numbers that cause x squared minus 9 to be 0? 3 and negative 3, right? Okay, we already did that earlier in the problem. So basically, we're undefined at 3 and negative 3. Okay, now these are the three numbers that you're going to use in your sign chart. Okay, and it's all about doing a sign chart to determine where the function increases and decreases. Okay, so when you get the first derivative, set it to 0. That'll give a critical point you're going to use in your sign chart, figure out where it's undefined. Okay, so now we're ready to put together our sign chart, and then this will go like this. Okay, so what we're going to do is draw a number line. And we're going to put x equals 0. We're going to put x equals 3. And x equals negative 3. All right, now what happens is the derivative is undefined here, so I like students to usually just put ND for no derivative. Okay, there's vertical asymptotes there. That's what we found earlier in the problem, so we have that. And then this part right here is where the derivative is 0. Okay, like that. Okay, now when we do our test points, you can do this as much as you can in your head, and I'm going to kind of show you what I'm doing over here. So the first derivative, you don't necessarily need to write all this stuff down, but here's the first derivative. And you want to do everything you can to make this go as simple as possible for yourself. So we're going to do a test point here. What's a good test point below negative 3? Negative 4, okay, that's what I thought of. It's up to you, whatever you want to choose. And you plug it in. Well, the way I do this is like this, and you can do this kind of stuff on scratch paper. Does it make sense that the bottom is always going to be positive? That's a good question. What are you doing? You're squaring something, right? Okay, if you don't see that, you can crunch out the details, and that's what you're going to find. So I'm going to go over here, and I know my denominator is positive. The numerator would be negative 58 times negative 4, so that's a positive. So this means this is a positive over a positive, therefore it's a positive result. Now usually we just put a bunch of plus signs, because what that means is no matter what that test point is, the derivative's positive. Okay, and it's all arithmetic, and you can do all that on scratch paper if you want to. Okay, all right, let's go here. What's a good test point in the next place? Maybe negative 1, maybe negative 2. Okay, so again, it's going to be a positive denominator. It's only the numerator that matters, so if we do negative 58 times negative 1, we get a positive. So that's positive over positive again, so that means that's positive. Plug your test point into your derivative and figure out if it's positive or negative. Do it in your head if you can. Write it out, whatever it takes. Use your calculator if you have to. Okay. Now we go here, test point of 1. All right, again, the denominator is positive because you're squaring something. Okay, so what we do here is just take the numerator, negative 58x, plug in positive 1, you get a negative number. Okay, so what you would get is a negative over a positive, therefore that's a negative like that. Okay, does everybody understand what I'm doing? Okay, plug into your derivative, okay? You can do whatever you have to do. I mean, work every step out if you have to. But with practice, you can learn how to do a lot of this in your head. Now let's go to 4. Okay, again, positive denominator. Negative 58 times 4 is negative. So it's negative over positive, so it's negative again like that. Okay, that's how you do that then. Okay, so how do we determine where it increases? That's going to be what? Where the derivative is positive. Okay, how about decreases? What is that? That's where the derivative is negative. Okay, that's what all that information tells you. Okay, so we're ready now to name this then. So we're going to increase from negative infinity to negative 3, and then from negative 3 to 0. So I'm naming that with the x values. Okay, you have to chop off negative 3. There's no derivative there. The derivative doesn't exist there. There's an asymptote there. Then we're going to decrease from 0 to 3 union 3 to infinity like that. Okay, so that's what we got there. All right. Okay, now the local min and max, you have to think about what this sign chart is saying. Now I'm going to scroll this up at the top here a little bit, and this is really what's going on in the problem. Now you don't have to write this down, but we have basically what you have is the function is decreasing when you're to the left of negative 3. But what that's going to mean is it's going to probably do something like that. Then it's going, whoops, hold on, it's increasing. So the function's going to increase. So it's probably going to kind of do something like that. And then from negative 3 to 0, it's also going to increase. So it's probably going to do something like that. And it's going to go to infinity around the asymptote. So there isn't any minimum there. And then the function's going to turn around and decrease here. And then it's going to decrease some more here. Okay, you got to think about, since these are asymptotes, the only possibility here. So there isn't a min or max there, but that right there is a maximum, isn't it? Okay, so the function basically changed from increase to decrease. That's what a maximum is. So that's the only thing that you're going to have, is you're not going to have a minimum, but you are going to have a max at x equals 0. Okay, I'm just going to put the x value like that then. Okay? All right? Does that make sense? Okay? The sign chart will tell you mins and maxes. It's just where the sign changes. Okay? It's got to be a point on the graph where the sign changes, either from plus to minus or minus to plus. That's the only place that happens. Okay? All right. Now what I'm going to do, we're going to put together the sign chart for the second derivative, which is very, very similar. Okay, so let's see. I'm going to write down the second derivative on this. I'm just going to kind of write this down up here. So the second derivative was 174 times x to the second plus 3 over x to the second minus 9 to the third. Okay, I think that's what I had you write down on the second derivative. Okay, all right. So what we're going to do on this is the same thing. We're going to set, you want to set the second derivative equal to 0, and then you want to figure out where it's undefined. Okay, so really what you do is this, and you can you just take that second derivative like it is, and you set that equal to 0. Okay, now that's an equation you have to solve. Well, you can do this too. What you're doing is, and you can do this in your head, you're going to multiply both sides by the denominator to get rid of the fraction, like that. But you can bypass this, because what's going to happen is you just end up with the numerator set equal to 0. So we got to solve that equation, and that will give us places on our sign chart that we're going to analyze the concavity. Okay, well, the easy way to solve this one is probably divide both sides by 174. That will end up giving x to the second plus 3 equals 0. Move the 3 to the other side, so that's x squared equals negative 3, like that. Square root of both sides, what does that tell you? Square root of a negative number, so what does that tell you? We don't even pay any attention to it, okay? That's not a real number, so we don't worry about that, okay? So that doesn't matter, all right? But it's worth trying, because you wouldn't know unless you tried that, okay? So the other question would be, is the second derivative, and you don't have to write this down, I'm just trying to write down what I'm asking you here, is the second derivative undefined anywhere? That's the other question. Is there some place where it's undefined? You can do that in your head. Look at the denominator. Is there any place that makes the denominator 0? 3 and negative 3 again, right? So what you would have is you would be undefined at 3 and negative 3. So when we do the sign chart, we're only going to look at 3 and negative 3. We're not going to look at anything else, okay? But we went about this basically in the same way. All right, so here's how your sign chart's going to go. And I realize this is kind of messy. So we're going to have negative 3, and we're going to have 3. Okay, and I'm going to erase a few things so I can kind of do this at the side here. Okay, so now what we got to do is we just do test points. So we're going to do, like, say, negative 4, maybe 0, and maybe 4. Okay, and again, you don't have to write this down unless you want to. So if I do the second derivative at negative 4, I would have 174 times negative 4 to the second plus 3 all over, and then you got to crunch this out now. That would be negative 4 to the second minus 9 to the third, like that. Okay, so when you're doing this stuff on homework, I mean, you got to figure it out some way. You could put that in your calculator, or you could do as much as you can in your head. So here's kind of the way that I would look at this then. This is really 174 times 16 plus 3. The denominator is 16 minus 9 to the third. Now that's good enough, okay? What's the numerator, positive or negative?
Positive.
That's all that matters. What's the denominator, positive or negative?
Positive.
That's all that matters. Don't waste your time. So that's positive over positive. That means that you're positive in that region, like that, okay? And then just do the same thing over and over again. Take the second derivative at 0. That's 174 times 0 squared plus 3. 0 squared minus 9 to the third. Be careful. Okay, this is going to really be 174 times 3, and it's going to be negative 9 to the third. Okay, what's the numerator, positive or negative?
Positive.
What's the denominator? Careful.
Negative.
Negative. If you take a negative number and multiply it 3 times, you get a negative. So that's going to be positive over negative, therefore it's negative. Okay, you see what I'm doing? Okay, and I'm not doing all the arithmetic because I don't have to, okay? Well, I'm not going to do the other one. What would happen on the other one is you would get positive over positive, so you would get that. Okay, does everybody understand how I'm doing the arithmetic with test points? That's incredibly important in what we're doing now. You need to do that the best you can and get it totally accurate It's all arithmetic. Okay, so here's what this means. We're concave up here and there, and we're concave down there. Okay, so we're ready to put that together. So it goes like this. So concave up, we would say negative infinity to negative 3, union 3 to infinity. Okay, and then concave down is going to be between negative 3 and 3. Okay, so we got that. The sign chart. So what you're doing is taking that second derivative, test points, and using those test points. Okay, inflection points. Now the thing is, you may have already forgotten by now, but we have vertical asymptotes. We have vertical asymptotes at negative 3 and 3. So that means the concavity does change at negative 3 and 3, but that's not a point on the graph. That's an asymptote. Okay, so you don't have any points of inflection, and if you want to write this down, you can. It's because negative 3 and 3, the function's undefined, so we don't have that. Okay, having fun with this problem? This is kind of, like I said, this puts it all together. Okay, this is putting it every little thing that we've learned all together. So on the next page, we're going to wrap it up with a graph. Then we'll be done. Then we'll just check it and verify it on the graphing calculator. Students always say, why can't I just use my calculator? Well, you're in a calculus class. You're learning calculus. That's why. You can use it to check. Okay. Not teaching you to be a button pusher. Okay. So here's kind of what we have on this then. All right. So let's get this graph put together. And what you want to go ahead and do is start with your vertical asymptotes. And I'll just kind of show you what to do. All the information's on the previous page, so I'll kind of scroll back and forth. Okay, so that was, one of the first things we figured out was we had vertical asymptotes at negative 3 and 3. Horizontal asymptote, we had one at 3 also. So a horizontal asymptote was y equals 3. Okay, so that was way back at the beginning of the problem. We had the asymptotes there. Okay. Now, this is basically what the sign chart said on this. I'm going to kind of write a little note on here now. Okay. And let me do this, and I'll come right back to this. I want to just be able to display that when I put this together. So I'm going to take a little picture of these sign charts. So now what you're doing is trying to put the whole thing together. Okay, the other thing I recall that we had was I think we had a y-intercept at 0, negative 2 ninths. Okay, we had that. So just kind of throw a dot in there like that. Okay, now this is what you're ultimately trying to learn how to do. Okay, so when you're to the left of negative 3, what's the graph doing? The graph's increasing, right? So it's got to go to the asymptote like that, and it's got to level off like that. So does it make sense that it would go like that? Couldn't be down here because the graph would have to go down towards the asymptote. Look at the concavity. Concave up. Is that concave up? Yeah. Okay, that looks good. Okay, now from negative 3 to 0. From negative 3 to 0, what's the graph doing? The graph is increasing. So it's going like that, and of course it would have to go through that y-intercept. You would increase, okay? Then it's going to start decreasing from 0 to 3. Does that look sensible? Graph increases, graph decreases, okay? Like that, all right? Now out here the graph decreases. So when you're past 3, the only way this graph's going to decrease is going to be like this, because it's got to approach the asymptotes like that. So let's put that in, and then we'll see if this makes sense to you. This is the last part of the problem, is just putting it all together. Okay, so it's going to have to go like this. The graph's going to have to do something kind of like this, right? And that matches this. The function's increasing and concave up. Okay, that's what the sign charts say. Then here we're going to increase, like it says. Okay, we're concave down also. Then we're going to decrease from 0 to 3. Like that. So does that match everything? Is that concave down? That whole thing's concave down, isn't it? Okay. And then out here, finally, we're going to be decreasing in concave up, so that has to go like that. All right, that's everything. That's the only thing that's possible on that. So right here, you're increasing in concave up. Here, you're increasing, decreasing, but the whole thing's concave down and concave up like that. So it's concave up, concave down. Problem done. I promise you, if you put that in your graphing calculator, that's what you're going to see. Okay? All right, let's do that, and then we'll take a break. Okay, so if you want to do this, you can do this with me. I'm just going to do this standard window, and I'm going to put this in. Now, when you put this in, make sure that you have parentheses around this. So it basically is going to go like this. We have parenthesis 3x to the second, and then plus 2, close parentheses, divide by, and then it was x to the second minus 9. So that's what we spent like the last 30 minutes analyzing, is that one graph, okay? So I think I got everything in right. Let me put that in a standard window. And let's see, I think I had an extra line in there or something too. Okay, that's it. Okay, I don't know, I think I have that extra thing in there. So that's it. Okay? Okay, does that look okay? What's the hardest part of the problem to you? I'm curious. Or is there anything hard? Probably the sign chart and the derivative. The derivative part's probably the biggest part of that's doing that derivative. Okay, okay. All right, well, let's go ahead and let's take a break for about 5 minutes here. And I'm going to look at a few other things in this section a little bit easier than that. But that's a big problem. This applications on this. Okay, so down at the bottom of page 5, this is stuff that we've learned before, but I'm going to just quickly kind of review this on a horizontal asymptote. Just give you a quick review because we're going to talk about oblique asymptotes a little bit. So basically, if the degree of the numerator is less than the degree of the denominator, then y equals 0 is your asymptote. Let's just write down an example of each one of these. Okay, so for example, we could have f of x equals x to the second minus 1 over x to the third plus x squared plus 2. Okay, the degree of the top is 2, degree of bottom is 3, therefore the horizontal asymptote is 0. If you did the limit of that function as you went to infinity, you would get 0. You could do L'Hopital's rule, like I did in class last time, you'd get 0. Okay. The next one is what happens when the degree of numerator and denominator are equal. That's what happened on the last problem. An example of this would be something like g of x equals, let's say, 4x to the second plus x plus 2. And let's say something like 2x to the second minus 3. Okay. Well, what you would get on this is the horizontal asymptote would be y equals 4 over 2. Okay, so anytime the degrees are the same, then that's your asymptote right there. Okay, so those are the things that we've learned before. We haven't done much with oblique asymptotes. We're going to do a little bit more with that in this section. Okay, those are quick rules to know. And then what happens if the degree of the numerator is bigger than the degree of the denominator, and it has to be bigger by 1 unit. That's all we're going to look at is bigger by 1 unit. Then you have an oblique. So an example of this would be something like g of x equals x to the third minus 1 over x to the second plus 1. The degree of the top's 3, degree of bottom's 2. It's 1 bigger, therefore you have an asymptote that slants. That's called an oblique asymptote. Okay, and that's where we're going to focus on is what the oblique asymptotes are then. Okay. All right, so that's probably good enough, all right, just kind of as an overview. You want to make sure that you review those rules. Okay, on the next page, I'm going to show you how to take a function and figure out its oblique asymptote. All right, so what you want to do is you want to basically just do the limit as x goes to infinity. So you just got to work out a limit on this. And you can graph on your calculator and tell if you're right or not on this. So what we're going to do on this example is we're going to do the limit as x approaches infinity of x plus 1 over x. With a little practice, you can kind of do this in your head, okay? Well, what happens on this is the way that you end up doing this is you just kind of in your mind think about what happens if x goes to infinity. Well, what you would end up having is you would have infinity plus 1 over infinity, like that, okay? And remember, we talked about this last time. This is super important. Anytime you have a number divided by infinity, where does the graph go? Where does it get close to? 0. Okay, sometimes students don't understand that until they play with their calculator a little bit, but all I'm saying is this. If I randomly pick a number on the calculator, like 9, and divide it by a bigger and bigger number, I get close to 0. And it doesn't matter what the size of that numerator is. The numerator could be a googolplex to the googolplex million billion power, if that's such a number. If you divide it by something infinitely bigger, it goes to 0. It always does. So what happens is this thing goes to 0, so that means the answer to this limit is infinity. So here's what that means. That means is that if x goes to the right, the graph gets infinitely big. That's what that's saying. Now the answer to the oblique asymptote is basically what's left over, okay? So basically what happens is the 1 over x, that part goes to 0, you're left with y equals x. Okay, so the part that goes to 0, just cross it out and ignore it. Everything else that's left over is going to be your oblique asymptote. Okay, now let's put this in the calculator because it'll help you to understand what I just did and what we're after here. So please do this with me. If you brought your calculator, let's just put this in, and just put it in like this. You just put in x plus 1 over x. Okay, then I want you to do this. I want you to also go to y2 and just put x in because that's the oblique asymptote. So you just want to put that in, do a standard window, and we'll see if this helps you make sense out of what I just did. The graph in blue, that's the graph. The one that goes in red is the oblique asymptote. So I want to show you what happens. When x goes to infinity, what does that blue graph do? It gets close to that slanted line. That's what an oblique asymptote is it just means the graph is going to approach it. Just kind of like a horizontal asymptote, but it's the same concept. Does that make any sense? Okay, that's what we just found, and that's how you can verify that that's a right answer on the problem. This is by looking visually on the graphing calculator and seeing if that gives you what you expect to get. Okay, so we'll do the same thing on each of these problems. The next one, same thing. We're going to do the limit as x goes to infinity of negative 3x minus 1 over x squared. And with a little practice, you can do this stuff in your head. You really can, okay? So here's the idea. This part right here, what would happen if you did negative 1 over infinity squared? Where would that go? That goes to 0, right? Anytime you have a number divided by infinity, it goes to 0. So that part right there goes to 0. How about this part right here? Negative 3 times infinity, where does that go? Does it go to positive infinity or negative infinity? It goes to negative infinity because it's a negative number. Okay, all that means if you take negative 3 times a bigger and bigger and bigger number, it just gets to be a smaller negative number. So what's happening is this thing's going to negative infinity while that goes to 0. So you can just kind of in your mind just block that off. You can do these problems in your head. The part that goes to 0 is sort of gone when x goes to infinity. The oblique asymptote is y equals negative 3x. You're always going to get a linear function when you do these problems. That's the way it will always work out. Put this in your calculator. That'll, again, I think, help you understand visually what's happening on these problems. That's the only way really to make perfectly good sense of this. You just look at the graph. Okay, so let's put in the graph was negative 3x. And what was it? Minus, I wrote over that, minus 1 over x squared. And then also you want to put in your oblique asymptote. So negative 1 over x to the second. And then we'll put in y2, we'll put in the negative 3x. and we'll see if this looks visually pleasing. Okay, let's see what happens. The blue is the graph. Okay, so here's what happens. All right, when x goes to infinity, what's the graph doing? It's going to negative infinity, and it's getting close to that asymptote. It'll never touch it. If you zoomed on a little piece of the calculator there, those things would be almost touching each other, but they never do. They just get closer the further out you go. Does that make sense? Okay, these problems are pretty easy to do. You can do these first two in your head, actually. Okay. Okay, so next one we're going to do this. So again, we're going to do the limit as x approaches infinity of negative 2x to the second plus x plus 1 all over x. Now what you're trying to do to get that oblique asymptote, you probably need to break this up. And what's going to end up happening on this problem is the numerator is going to get infinitely small, while the numerator gets infinitely big. Now, we're not going to find the oblique asymptote that way, but you don't need to write this down. But if you replaced x with infinity, let me sort of explain conceptually what happens in this problem. Okay, the denominator is just going to be infinitely big. Agreed? Okay, x gets big. Now, what do you think? I'm going to ask you this question just to see what you think. Do you think the numerator would get infinitely big in a positive number or infinitely small with a negative? That's a great question to ask students.
Small.
Small. How come? Because if you square infinity, it kind of gets bigger faster, doesn't it? So this negative part right here overwhelms the rest. Okay? That's kind of a bizarre way to think of that. So this, you're going to get negative infinity on this limit. I'll do that, show you the correct way to do that in just a minute. So what you want to do is you want to split this up. So you want to write this like this. The next step, just write limit x goes to infinity of negative 2x squared over x plus x over x plus 1 over x. What I'm doing is I'm just tearing apart the fraction. Okay, it's got a single denominator, so you can chop it up. Well, this part right here, one of the x's cancels out, so that gives negative 2x. X over x is 1, and then the 1 over x we're just going to leave the way it is. Now that stuff you can process in your head, so the next step I'm going to write is the limit x goes to infinity of negative 2x plus 1 over x. Okay, now let's just see if we can do this in your head. I want you to catch on how to do this in your head. Which part goes to 0 out of what's left over? That part right there, right? That part goes to 0. That stuff there just gets infinitely big. So that part right there is your asymptote, okay? And you can do that in your head. It's just the idea is this thing right here goes to 0. Okay, you don't have to show anything on your paper. You know it goes to 0. So that means the oblique asymptote is y equals negative 2x plus 1, like that, okay? And then we're going to just do a little graph on this one and show you. Now see, that one you got to split up. The other two, part A and B, were already split up for you. So if they're not split up, you got to do it like that. Okay, that's how you find your oblique asymptote. Okay, so we're going to make a little sketch on this one. And just do this on the calculator. Let's see visually how this thing looks. So and you want to put in the original problem. You would want to put parentheses in the numerator, negative 2x squared. Whoop, I do that all the time. So negative 2x squared. I cannot do this. There we go, finally. Okay, negative 2x squared plus x plus 1 divided by x. And I'm going to graph this just kind of one at a time. All I want you to do is just do a rough sketch of this. It doesn't have to be perfectly beautiful and everything. So what I see is a kind of a graph doing something kind of like this. All right, kind of got something like that and something kind of going like that, sort of. Okay, you actually have a vertical asymptote at x equals 0, like that. Okay, and then if I put in the second one, that will be a line. So if you put in negative 2x plus 1, and then we'll just do that oblique asymptote like that. Okay, then you can just kind of do this. So this one has a y-intercept of 1. It's a line, so it's a linear function. Has a slope of -2. That's your slope. So what should be happening is you're going down 2 over 1. So it kind of does something kind of like that. That's not a real great graph, but it kind of gives you the idea. Okay? So that's the idea. All right, so that's what you do to find an oblique asymptote when you have that particular type of problem. Split it up on part C. That's the best way to do that. Some of these problems are already split up, and it's easy to do in your head. Okay? All right, so a real quick question, and then we'll do these applications. So if you had something like y equals -2x plus 1 over x in your head, tell me what the oblique asymptote is. Y equals -2x, okay, because this thing right here is the one that goes to 0. Yeah.
I do have a question. So on the problem you did with the graph,
yep.
why does the second portion of it, it looks like it has like a vertical asymptote also.
It does. It has a vertical asymptote at x equals 0.
Oh, okay.
And the reason is because, see, the function's undefined. The denominator, when x is 0, you have a vertical asymptote. Okay. So, yeah, it does have a vertical asymptote. Okay. But the oblique asymptote, we're interested in what the graph does as you go to infinity, see. That's the idea. So, yeah, you're right. Okay, now let's see. Application. So I want to finish up with this application. This is kind of the standard application we teach students in this level of a class. So we're going to look at what we call the average cost. This is the average cost formula. And C bar, anytime you see a bar, that means average. A lot of you might take a business stats class someday. When you take statistics, X bar stands for the average, okay? So what you do is you take the cost function you're given, and then you just divide by X. So we're going to go ahead and just do the average cost function. So all you need to do on that is take the function I gave you, 7,500 plus 65x plus 0.01x squared all over x. That's all you do to find an average cost function, because you're dividing by the number of things that you're producing. X is how many things you're producing. So if we're going to do the oblique asymptote, what do I need to do? Separate it, split it up just like the last problem, and then do the limit. Exactly. So we're going to go ahead and do that right now. So you would just have 7,500 over x plus 65x over x plus 0.01x squared over x like that. Okay? And just simplify. So you have 7,500 over x. The x's drop out there, leaving you plus 65. And then the last one of the x's crosses out, giving you 0.01x the second like that. Okay? Now, what you technically want to do on this then, I put the wrong thing on there. So that's one of the x's crosses out, so it gives that. Okay, well, let me see if you can just do this in your head. Can you tell me what the oblique asymptote is now that it's split up? 65 plus 0.01x. So what happens to this thing when you go to infinity? Okay, that goes to 0. Exactly. So the oblique asymptote is that part right there. Okay? You're going to end up with some part that goes to 0. So you end up with a line. So the oblique asymptote would be y equals 0.01x plus 65. Okay, does that make sense? Okay, that's your oblique asymptote. So what that's going to tell you is the graph, when you go to infinity, when the graph gets bigger, it's going to approach that line that's slanting, and that's a positive slope, so that line's going to go up like that. That's what's going to happen, okay? Okay, go ahead and repeat what I just did, okay? I'll give you a couple of minutes to do this problem. There's nothing to it. I want you to know how to do that. Then we'll wrap up with one application on the next page. So what you want to do is do your average cost function. Go ahead and do that. And then you can do the oblique asymptote in your head if you want to. And you'll have to split this up. This is the same concept as the last problem, basically. You can actually just kind of split it up in your first step if you want to, so it doesn't matter. Okay, got an answer? What's your answer? 0.4x plus 340, exactly. Nothing to it. Okay, that part right there goes to 0, and this is what's left over. So that is your oblique asymptote. Doesn't matter what order you write those two numbers in either. So that's a line, that's a linear function. Okay, that's the idea. All right, questions on how I'm doing an oblique asymptote? That's the easiest part of the section. Okay, let's do this last application here and wrap this up. And so what we're doing on this is we have a total cost of producing bikes is this. This is a cost function. So what we're going to do is we're going to do these things. We're going to find the average cost function, the marginal, I think that's marginal average cost function, oblique asymptotes, graph, and then we're going to find what we call the minimum average cost. Okay, so go ahead and start by doing the average cost. So you can break this up, and when you do an average cost, if you want to save yourself a step, you can just go ahead and divide each part by x if you want to. That's what I do. Okay, so we get that. So it looks like when we do that, the answer is going to be c bar of x is, and I'm going to go ahead, since we're going to do a derivative in the next step, I'm going to go ahead and have you write that as 500x to the negative 1. Okay, and then the x's cross out, so that's plus 2. And then one of the x's crosses out, so that's 0.2x like that. So that would be your cost function. I'm just writing the x to the negative 1 because of the derivative that we're going to do in the next step anyway. Okay? All right, so remember marginal, we've learned that. That means take the derivative. So we're going to do the derivative, first derivative. So we can do this in our head. We're going to do c bar prime of x. So you want to go ahead and do that. It's a real simple derivative. It's this power rule. Bring down the negative 1. So that would be negative 500, x to the negative 2. Derivative of 2 is 0. And the derivative of 0.2x is 0.2. Okay, so you would end up giving the marginal average cost is given by the function negative 500 x to the negative 2 plus 0.2. Okay, so that's the calculus involved like that. All right? All right, so let's do the oblique asymptote. The oblique asymptote, again, you can do in your head. So we have c bar of x really was equal to 500 at x plus 2 plus 0.2x. Okay, so remember this thing right here goes to 0. So the leftover would be your oblique asymptote. So the oblique asymptote is going to be y equals 0.2x plus 2. All right, any questions so far? Derivative's simple on that. You've done a lot more complicated derivatives than that. Okay, so we're going to graph, and we're going to do a minimum average cost is what I want to do on this then. And we're going to do this on the calculator. So what we're going to put in is these two things. Okay, so you want to put the average cost in. The average cost is this thing I have in yellow, and you can put in the negative exponent, doesn't matter. I'm going to put in 500 x to the negative 1, and then plus 2, and then plus 0.2x, like that. We're going to also put in the oblique asymptote, which is what we just got, so that's the line 0.2x plus 2. All right, I'll kind of slide this over here so you can refer to what I'm doing if you need to, okay? All right. Now, for a viewing window on this, let's see. We're going to go ahead and when we draw our graph, I'll give you kind of a viewing window to do on this. So go ahead and just draw a corner graph. Make sure you get a perfectly straight line like I just did. It's so hard to draw a line on this thing. Okay, so let's go out like to 50 and 100. And maybe just kind of scale by 10. 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, and we got that. And then I think I'm going to do the y-axis up to 500. You have to kind of play with your calculator to get a fairly good viewing window like this then. Okay, it's always good to label what all this stuff means. So this is, I think this was X bikes. And then this is average cost. And then that will be in dollars. Okay, if you're a business person, you want to tell me what everything means in the graph then. Okay, well, what we're going to do is just, get enough points to get a fairly reasonable graph on this thing then. So you do need to set your viewing window on your calculator like this. So on the window, we're going to go 0 to 100 on the x-axis. Scale by 10 is a logical way to do that. For the y, we're going to do 0 to 500. And scale that by 100. And then we'll kind of take a look at our graph. And then we're just going to sketch it. Okay, I'm going to get a couple of key points like that. So you got that graph like that, and you can see the asymptote coming up like that then. So now what I'm going to do on this is just kind of have you trace out a couple of points. So it doesn't really matter. I'm going to do this. I'm going to type trace, and I'm going to like trace at maybe 10 or something. You can also use your table of values. So I've got a point 10, 54. I'm just going to have you trace out a couple of points and label it. I'm going to go all the way out to 100. So if I trace at 100, that will give me 27. So I'm going to go out here and say that I have a point 127. Okay, and then the rest of that you can just sketch to get the idea. Now what's going to happen on this problem is it is going to hit a minimum and start kind of increasing, so it's a little hard to see that. So that's what's going on. I'm not going to have you do the oblique asymptote. That doesn't make that much difference to have that on your graph then, okay? So that's what you want to get for your graph, and that's good enough. Now what we're going to do is find the minimum average cost. So what we're going to do on this is basically do this. We already found the first derivative. When we found the first derivative, we had negative 500 x to the negative 2 plus 0.2. Okay, if you scroll up earlier in the problem, that was the marginal average cost. So what you're going to do is you're going to set that to 0. We're going to solve this equation, and then we should have where our average minimum is then. Okay, so I'm going to just write this like this. This is negative 500 over x squared plus 0.2 equals 0. You're finding a critical point on the problem then, okay? So let's see, the easiest way to do this would be, to me, would be to move that to the other side. So you would get 0.2 equals negative 500 over x squared, like that, okay? Put that over 1, cross multiply is a pretty easy way to do this then. So I'm going to cross multiply this, so I get 0.2x squared. Oh, what in the world did I do? Did I do something wrong on this? Yeah, okay, so yeah, that's positive. I move it to that side, so that becomes positive. I was seeing I was going to get an imaginary number, and I knew that wasn't right. So I have 0.2x squared equals 500. Divide both sides by 0.2. That gives x squared. On the calculator, that would be 2,500. If you take 500 divided by 0.2, you get that. Square root both sides, that is 50. Okay, so what you end up getting is when x is 50, that's where you're going to end up doing the minimum. And you can tell by your graph that it's a minimum on there. So what you want to put on your graph is this number here is the minimum like that, and then you would have to just trace that out like this. So on my calculator, if I trace it 50, that should give the minimum average cost, okay? So that's 50 and 22, like that. So you know it's a minimum because you can tell by looking on your calculator. So the place where the derivative is 0 is going to be, in this case, is going to be where that minimum is. Okay, that's how you do it. Okay? So once you get that first derivative, set it to 0, that's how you'll get that put together. Okay, does that make sense?